In this video, we will be reviewing over magnetic fields, not only their physical properties, but how one goes about solving magnetic field problems in physics. During the course of the video, you will be given 4 important formulas for solving magnetism. This will be related to 2 of your Unit 13 homework assignments, the particles in a magnetic field, and force on current carrying conductors. You will learn to solve for the force of magnetics. You will learn to solve for magnetic field strength, for the velocity that a charge is traveling, the length of wire or cable that is carrying the charge, and the current that is passing through the cable. Reviewing back over magnetic fields, when moving through a magnetic field, a charged particle will experience a magnetic force. This force has a maximum value when the charge moves perpendicular to the magnetic field lines. This force is 0 when the charge moves along the magnetic field lines. One can define a magnetic field lines in terms of magnetic force exerted on a test charge moving in a field with the velocity. The unit for magnetic field lines is the Tesla. Its abbreviation is a capital T. One of the formulas that you will be asked to know in order to solve for your problems is right here. Now, I typically use this in a little bit different arrangement, and let's show you the arrangement and what each of the components is for. All right, now as we look at this equation, and again, the way I've written it down is just it's the same formula, it's just I prefer this form. So we have our magnetic force. Our magnetic force will be in units of newtons. Now this right here, the capital B, this stands for our magnetic field strength. This will be in the units of Tesla, which is the capital T. Our Q is our charge, and remember that's in units of coulombs. Don't forget that if a charge is not given, is the problem referring to an electron, and do you need to use the standard charge for electron? Your V is your velocity. Many times they will give you the velocity in kilometers per hour, and you will need to convert this over to meters per second. And then you will be given an angle, and so you would have to take the sine of that angle. The second of your equations you need to know is right here. You can copy that down, but I'm going to talk about that on my next slide. What I want to go over with you on this particular slide is the equation for magnetic force when we deal with length on a wire. That's why we had this right here. So when we talk about that, what we can do is we can find a direction of a force. And so the direction of the force, we can look at it in terms of this right here, where we're using the right-handed rule. And with our right-handed rule, we're going to use our thumb showing the direction of current. We will have B being where the fingers are located, and remember that's going to be your magnetic force field. And then your F right here is going to be your force of magnetics. And so you'll notice that your force is perpendicular to the plane of I and B. And then right here you can see where that angle, that sine angle of theta is located. So just to give you that visualization of what we have. So that when we look at our angle here, our theta angle, it's between B, our magnetic field strength, and I, our current. Here are the other 3 formulas. let's talk about each of these. Now let's start off with this one right here. Now on this one right here, we've got our magnetic force, and this should have the force magnetic right there. And that is equaling, and this should be magnetic right there as well. That's going to equal our B, our field strength, again in Tesla, times our current, which is in amps, times our L, and our L is going to be the length of the wire, and that's going to be in meters. So if we are solving one of these right here, we're typically using this on a current carrying conductor where we're trying to calculate the magnetic force. We've got our magnetic field strength here, we've got our current given, and then we've got some length of our wire that we're using. Now, if in those same problems you were given your magnetic field strength, you were given a current, and you were given the length of the wire, but you're also given an angle, then you're going to use this formula right here. So you would take your BIL times your sine theta would equal your magnetic force. On that very first page, I gave you this formula right here, where we had our magnetic force equals our charge times our velocity times our magnetic field strength times sine of theta. So we would use this formula right here when we're looking at calculating our particles in a magnetic field if we're given a velocity. If we're given a velocity and no angle, we would use this formula right here, where we would have our magnetic force equals our charge times our velocity times our magnetic field strength. The magnetic field strength can have set values, and so these are some different standards or values that you can run across. You will not need to write these down. Your B value will either be given in the problem or it will be the component you are solving for in the problem. Now these are not difficult problems, but let's go ahead and look through a few examples. So we have a liquid is activated by a magnetic field with a magnitude of 0.08 Tesla. Now this right here is going to be our B. Okay. And then it also, a Tesla can be converted into, it's a Newton amp times meter. So you could see how we can use this as our conversion factors, our canceling out. What force will the particle with a charge? Now we've got our charge right here. What force? That's our magnetic force. And then we'll notice that we have a velocity here. Now our velocity is in centimeters, so I'm going to convert that over to centimeters per second. I'm converting that over to meters per second. I have all of the components, so I can use my formula. My magnetic force equals B times Q times V. I've isolated the B. We can plug in, we can solve, and we would get our answers. Magnetic force would be in newtons. Our Tesla would allow us to cancel out our amps and our meters. Now here we have one where we have a length of wire. So in this example, it says that we have 1,000 Tesla magnetic field. So we've got that identified here. It was obtained, and let's see, we have a 25 centimeter long wire. We're going to go ahead and convert that over to our meters. So we've got that converted there. And it says the magnetic force on the wire was 1.6 times 10 to the second, and it's asking what is the current. So we're going to come over and we'll use the formula. The magnetic force equals BIL, and we've just isolated the I, put our numbers in. You'll notice that our newtons and our meters will cancel out of our Tesla, leaving our amps. And our magnetic problems on these two assignments really does not get any more difficult than this. You may have an example that has an angle, and then just use the appropriate formula and you'll be fine.